Section 7.3, Linear Discriminant Analysis, LDA. The LDA is a method to find a linear combination of features that characterizes or separates objects. The LDA is a projection method that can be used for classification or dimensionality reduction. The LDA is sometimes called Fisher's LDA because Fisher invented. Now, here we have LDA objectives. LDA objective is to perform dimensionality reduction. And PCA also does that, so it's not really new. However, we want to preserve as much of the class discriminatory information as possible. So it is new, and it's worth considering it. Here, this is basic terms. Consider a pattern classification problem where we have C classes. So for each class, we assume there are nk samples, k's from 1 to c. Now, xk is collection of the point samples, and each one has a d dimension. So all whole data set is in d by n dimensions. So one column, each column is representing a sample. And LDA seeks to obtain transformation of x to z through projecting the samples in x onto a hyperplane with a dimension c-1. We'll see detail later on. Here, consider a projection. Fisher's LDA as a classifier can be considered as a projection method. And for simplicity, we start with C classes. So the projection is always c-1 dimension. So once C is 2, then the projection will be onto a line. And c-1 is 1. So one-dimensional space is a line. Okay. Here, we'll try to find the projection vector W such that for each point, if we apply dot product, try to get a dot product, then we'll get a constant. After projection, each point will be projected into a point in a line, and that is a projection. So the objective of Fisher's LDA is to find the projection vector so that after projection, they are well separable. Okay, let's begin with some terms to define and to organize, to formulate the Fisher's LDA. Okay, of course we have to define measures. Yeah, the mean vector of each class and also in G feature space can be defined in this way. Mu k is the mean of a point in class K. So the points are added and divided by the number of points. Okay, now in projected space, okay, we'll try to use here now tilde notation for projected quantities. Now, Z is projected from the points in case class. Now, after projection, we try to add them, and so that we try to get average value, mean value. But Z is the same as here W transpose X, so that we write in this way, so that now W is constant, not changing over the summation, so that first we make average over x, and then now apply dot product here. That means that after getting the mean of the points in each class and the mean can be projected, that is basically the same as mean of projected points, right? Okay, now we define distance between the projected means in this way. Just mu1 tilde minus mu2 tilde absolute value will be the distance. But that is the same as here in W transpose here mu1 minus mu2. Okay. If we try to maximize only the distance between the projected means, then we have some problem. Here, if we try to maximize this one, then it's the same as that. Here we have to choose a W parallel to mu1 and mu2, so that if you try to simply maximize the distance between the projected means, so that and that's now, if we consider this is the goal, then W must be parallel to mu1 minus mu2. That means here now the W must be parallel to that vector. Once points are projected into the line over there, then here some portion of data have projected values overlap each other from class 1 and class 2. So this projection is not really effective. Originally, these two are separated. However, after projection, they have overlap. Then now the projections are not really good. Here, now to avoid that, and Fisher proposed a solution. Now we try to maximize a function that represents the difference between the means, but now it is normalized by a measure of within class variability. That's called within class scatter. Now let's formulate it mathematically. Here, for each class K, we define the scatter. That is, in fact, the same concept with the variance. Now here, okay, and we try to, now that is the mean of the projected points, and that is individual projection. Now here, the difference is now squared and added. So it is a sort of a variance in each class. So on case 1, we are making this one, and for case 2, we try to make it this quantity and sum, so that this S1 squared plus S2 squared measures the variability within the two classes and after projection. And so that it is called within class scatter. So from each class, the variance is measured and added. We call it the within class scatter and after projection. Now, rather than maximizing just the distance itself, it's normalized by here the within class scatter. So here, maximizing that absolute value is the same as just maximizing here square of it. So that is square, and it doesn't matter anyway. Once this distance is maximized, then its square also will be maximized. So rather than simple distance maximization, we try to make the objective function now here normalized by within class scatter. That means that to maximize this objective function, the distance between projected means should be as large as possible, and also the within class scatter must be as small as possible. Now, usually when you define here the objective function with such fraction, and then bottom, the denominator is more sensitive, so that the solution will be more toward the bottom, so that this, once you solve the problem, then W, the projection vector, is now try to minimize this denominator. Okay. So here, for example, for that one, if you try to make a projection along that direction, so that this is a projection vector, then here variability within class will be minimized, so that this bottom portion is minimized, but yet the top is now has large enough distance. Once it is projected along this projection vector, then it's well separated. That's Fisher's idea. We'll try to solve this objective function mathematically in the second part. Thank you.